Hey guys, today's video is about proximity measures for numeric data. I'll introduce Minkowski distance of numeric data in this video. To recap, there are two steps to measure the dissimilarity for numeric data. The first step is normalization. You can find a video for normalization in my channel. The second step is Minkowski distance. Minkowski distance is not the only measure you can use, but it's quite popular in data mining algorithms. Since numeric data is essentially composed of numbers, we require some mathematical ways to measure the distance. Although we will see a lot of math involved, each formula has its own meaning. I hope you can understand what each formula represents in the real world, not just memorize them. Let's get started. Minkowski distance is a general method used to measure the dissimilarity between two objects. Say, we have object I and object Z. Each has P attributes. The formula goes like this. We add up the absolute distance of each attribute to the power of h, and take the order h roots of the number. The h here is flexible. You can plug in any number you want. That's why I say Minkowski is a general method. However, there are three numbers commonly used: 1, 2, and infinity. When h is 1, we call it Manhattan distance, or Hamming distance, or city block distance, or L1 norm. The formula is super simple, just the sum of absolute difference of each attribute. When h is 2, we call it Euclidean distance, or L2 norm. Does the formula look familiar to you? It's actually how we calculate the hypotenuse in a triangle. If you think about it, the hypotenuse in a triangle is the shortest distance between 2 points, which is also what Euclidean distance measures. When h is infinity, we call it Chebyshev distance, or supremum distance, or the uniform norm. The formula is not so distinctive because we can't directly replace h with the infinity. Instead, we have to take limits for h to approach infinity. I won't go deep into the mathematical calculation. It turns out the Chebyshev distance is just the maximum distance of all individual attribute distances. It's mostly involved in the calculation of minimum movement required to achieve certain goals, but it's only used in very specific cases. Let's look at an example. We have these two data points, one at the location 2, 2, another at 4, 5, and we want to measure the distance between them. We start with Manhattan distance, which is a special case of Minkowski distance with h equals to 1. The distance in the first attribute is essentially the difference between the x-coordinates of 2 points, which is 4 minus 2. In second attribute, the distance is the difference between the y-coordinates of 2 points, which is 5 minus 2. In this case, the 2 points are on a two-dimensional surface, so we only have 2 attributes. Then, we add the individual distances up. The Manhattan distance between 2 points is 2 plus 3, which is 5. In fact, Manhattan distance is not intuitive, right? It doesn't measure the shortest distance, which is how we typically think of distance. However, Manhattan distance is commonly used in categorical or discrete data, since this type of data doesn't have the numeric property. It doesn't make sense if we try to do complex mathematical calculation on discrete or categorical attributes. Therefore, simple deduction is the best choice we have. Next, we use Euclidean distance to calculate the distance between these two data points. As we said before, Euclidean distance measures the shortest distance between 2 points. In this two-dimensional surface, we basically calculate the hypotenuse in an imagined triangle. That is, we sum up the square of individual attribute distance and take the square root of this number. So, The Euclidean distance is the square root of 13. Euclidean distance is intuitive, since we usually mean the shortest distance when we talk about distance. However, Euclidean distance doesn't work well in high-dimensional space due to the curse of dimensionality. I won't go deep into this, but it's basically that in high-dimensional space, the thing doesn't work like what we see in low-dimensional space. In 2 or 3-dimensional space, we find the shortest distance reasonable. However, when the dimension is much higher, the Euclidean distance becomes nonsense, so we preferred using Manhattan distance in high-dimensional space. Last, Chebyshev distance is the maximum of all individual attribute distances. You may recall we have solved the individual attribute distances when calculating Manhattan distance. So, what we do now is finding the maximum among these distances. In this case, Chebyshev distance is the maximum of 2 and 3, which is 3. Before ending this video, I want to summarize the pros and cons of each distance measure. Euclidean distance is the most common measure and is intuitive, but it doesn't work well in high-dimensional space due to the curse of dimensionality. Manhattan distance is suitable for categorical and discrete data, as well as for the numeric data in high-dimensional space. However, we typically think of distance as the shortest distance between 2 points, which is not what Manhattan distance calculates. Chebyshev distance is the maximum distance along one axis. It's not common in practice. You should only use it when you are certain that Chebyshev distance suits the case, such as the warehouse logistics. So, that completes our discussion about distance measures for numeric attributes. Thank you for watching my video and see you next time.